In this video, we're just briefly going to recap the stages we looked at because we've done some diving into some details, and it's, I think, appropriate at this point to take a step back and just remind ourselves of the steps. We were looking at a temperature distribution on a square plate with some environmental conditions, insulated walls, and various temperatures on the outside. And we're interested in what the temperature in each of these cells would end up being once it reaches a steady state. And what we motivated that by was looking at the net heat flow into each cell. And we said that heat flow, when you added up positive and negative components, everything has to cancel out, so there's no net heat flow into or out of one of those cells. And that's going to give us that steady state behavior. When we looked at the physics then and the equation, which involved our heat flow being approximated by some element to do with the material, some element to do with the cross-sectional area, and the derivative of the temperature with respect to space, which we managed to package this way, it ended up honing in on the change in temperature between different cells. There's a prime there that shouldn't be there. The temperature difference between adjacent cells. Not diagonals. It's important not to include those because in those cases the area is technically zero between any of those diagonally connected elements. So all we have to worry about are up to 4 adjacent cells in these maps. When we looked at some elements like T1, we saw that it had 3 neighbors, 1 taken away because of the insulated wall. And so we ended up with a delta T that had 3 T1s in it, and the way we chose our signs, that ended up being -3 T1s, plus a T2, plus a T6, and plus a 20. Oh wait, the 20, when it got moved to the other side of the equation, turns negative. Same thing for T2. There's no insulated wall with T2, so it has 4 neighbors. We'd add a T1, add a T3, add a T7, T1, T3, T7, and we'd have an add 20 degrees for the outside. Oh wait, we move it to the right-hand side because we're going to put this in matrix form, so we have a -20 in that heat balance equation. And we can systematically write out the equation for every single cell all the way down to T25. We look at each cell and ask that its sum of the heat flows balance out or equal 0. When we put that into matrix form, we see some really nice structure in the matrix we're building. We see a -3 for T1 because it's beside the insulated wall. When we get to T6, the 6th row in this matrix, we see another -3, fantastic. We would see another one for negative at T11 because it again is beside the insulated wall and only has 3 neighbors. Everybody else, no matter where you look, has 4 neighbors that it's going to exchange heat with. So we have -4s everywhere else. There's 1s here, there's a band of 1s here. We'll talk about those and the relationship back to this matrix in a second. But the upshot is there's a really straightforwardly constructed matrix here. We've got our unknown vector of temperatures here. We've got our B vector here, and we can build this. We just need some for loops and a little bit of logic, but we can build this A matrix, we can build this B vector, and then we can use MATLAB to solve the system of equations in one line, and out will pop all of these unknown temperatures, and that is giving us a simulation of the temperature distribution in rich detail of this metal plate.